Hello everyone and welcome to this webinar about the general plasticity in SCIA Engineer. Before we start, a few words about the webinar progress. Attendee audio will be muted during the presentation. You can use the question box to ask questions during the presentation and I'll answer them when I finish the presentation, and the webinar will be recorded and posted on SCIA YouTube channel. Going to start with the introduction, there's 4 different plasticity criteria in SCIA Engineer. We will talk about how to adopt the finite element calculation to these plasticity criteria. Then we will move on to the practical part. So we will see some examples for walls, a beam on 3 supports, a base plate connection, and a beam column connection. The plasticity criteria is applied to all types of surfaces, plates, walls, and shells. What we should note that if we have a 1D element, a message will appear when we run the calculation that the plasticity will be neglected for these 1D elements. The plasticity is a nonlinearity, so we should run a nonlinear calculation to take it into consideration. It could be combined with other nonlinearities, but here we have one particularity. For the surface elements, we can have only one nonlinearity. For example, if we have a plasticity and a surface in compression only, the plastic behavior will be taken into account only. Another example, if you have a plasticity and membrane element, in this case, the plasticity will be ignored and the surface will be considered as an elastic membrane element. I'll explain the different plasticity criteria. The first one is the von Mises criteria. It's the most commonly used for ductile materials like steel, aluminium. The von Mises criteria takes into account compression, tension, and shear criteria to give an isotropic stress level the same in all directions. It does not indicate the type of the solicitation, whether compression, tension, or shear. Before plastification, the material has an elastic behavior, and to define the plasticity criteria of von Mises, we can use the von Mises stress or equivalent tensile stress sigma E. The material begins to plastify when sigma E reaches the yield point. On the right, the 3D representation is a circular surface, and below we can see the formula that's used to calculate the von Mises stress. Now we will talk about the second plasticity criteria, Tresca, which is also known as MSST or TG criteria. It's for ductile materials as steel, aluminium. The representation is a 6-sided prism of infinite length. It remains elastic as long as the 3 principal stresses remain roughly equivalent. It is a hydrostatic pressure regardless of the magnitude of the tension or compression. However, when one of these principal stresses becomes smaller or larger than the others, the material is subjected to shear. In such a situation, if the shear stress reaches the yield point, the material enters the plastic domain. Below, we can see the formula that's used to calculate the strengths, where SSY is the yield strength and shear, and SY is the tensile yield strengths. So now we have the third criteria, which is Drucker-Prager, which is similar to von Mises criteria. It's specific for materials with different yield strength in compression and in tension, and it's most often used for concrete, which is a material for which both normal stresses and shear stresses can determine rupture. Representation is a regular cone shape. We can see below the formula where M is SYC divided by SYT, where SYC and SYT are the uniaxial yield stresses in compression and tension respectively. The formula is reduced to the von Mises formula, where if SYC is equal to SYT, hence the equivalence between the two models. And now we will talk about the final criteria with more Coulomb, which is similar to Tresca criteria. It's specific for materials with different yield strengths in compression and in tension. It's most often used for concrete, soil, and granular materials. It's a regular conical prism and determines the angle of inclination of a conical surface. Below we can see the formula, and if SYC is equal to SYT, this formula is reduced to Tresca formula. For the practical part, how the von Mises criteria will be implemented in SCIA Engineer. Of course, SCIA is a finite element calculation program. The general von Mises formula, which is in a 3D environment, will first be calculated in form of principal stresses, using sigma 1, sigma 2, and sigma 3. These will be recalculated into principal plane stresses in two directions only, so sigma E as function of sigma 1 and sigma 2. This formula will be used in SCIA to calculate sigma E. On the right is a representation of the stress curve of von Mises and Tresca stresses in 2D environment. As SCIA is a finite element calculation program, it's important to see how this is involved in the calculation of plasticities. Rotational drilling is used at each node, allowing in-plane loading to be taken over, which means 6 degrees of freedom at each node. In the element area, 2 times 2 nodes are used. In the mathematical field of a numerical analysis, quadratic methods are approximations to numerical and integral values. The Gauss quadrature method is an exact quadrature method. Each Gauss quadrature point is realized by 9 Gauss-Labato quadrature points over the entire thickness of the element. So that an element with 4 nodes will have 2 times 2 times 9, which equal to 36 total quadrature points. Due to these points, the element can handle bending with great precision. In each of these nodes, the nonlinear model is calculated independently using the stress formula shown above, using sigma 1 and sigma 2. In the second part of this webinar, I show you how to activate the plasticity functionality in SCIA, how to define the property materials, and we will see some examples, 4 different examples. The first one about the walls, the second a beam on 3 supports, a base plate connection, and a beam column connection. What you should know that you should have the Sense.02 module, the advanced material nonlinear analysis, to be able to define plasticity in SCIA Engineer. After, in the project data, you should activate the nonlinearity, and in the nonlinearity, you should activate the general plasticity. To take into consideration the general plasticity, we should run a nonlinear calculation, of course, with nonlinear combinations. Before moving on to SCIA, you need to know that it's not enough to activate this function to take plastic behavior into account. You also need to modify the behavior of the material. We have 4 different behavior of the materials. You can see the elastic plastic without strain hardening, elasto-plastic with nominal plateau, elasto-plastic with linear strain hardening, and a true curve from tensile test results. The A, B, and C curves are implemented in SCIA Engineer. All materials are elastic by default. Plastic behavior must be applied to the desired materials. As you can see here, for example, for the steel S235, in the material behavior, we have defined an isotropic elasto-plastic vomicells behavior. In the input type, we chose the elastic plastic with hardening. The yield strength stress in uniaxial tension is fixed to 235 megapascal, and the hardening modulus is 2.1 times 10 megapascal. I've explained now the difference between behavior without and with hardening. For the first one, the stress is limited by Fy, the yield stress. For the second, there's an additional slope that can be manually modified in the material properties. By default, it's fixed to E divided by 10,000, but we can modify it in the property materials. With the Vomicells model, there is no defined limit to the strain value, which means that when the actual stress exceeds the maximum stress defined by the diagram, the latter is extrapolated from the last branch using a tangent. Stress and strain values must be checked in accordance to the Eurocode. The maximum deformation values given by the national annex is 5%. We'll move on to the examples. The first one, the three identical walls with the same geometry and the same thickness, which is 20 millimeters. We have exactly the same supports, which is fixed for the three of them. The only difference is the material. So here we have the steel 235. For the second one is the steel 275, and the final one is the steel 355 megapascal. We've applied the same load on the three surface elements, which with a value of minus 42.9 kilonewton per meter square. So now to define the plasticity in SCIA, you should go to the file, to the project settings, and in the functionality, we should activate the non-linearity and the general plasticity. I go to the materials to show you how to define also the behavior of the material. So for the three of them, we've defined exactly the same material behavior, but with a different yield stress. So in the material properties, you can see here the four different material behavior that we've seen before in the presentation. We had the elastic behavior, the isotropic elasto-plastic Tresca, Vomicells, Drucker, Prager, or more Coulomb. And in this example, we've used the Vomicells criteria, and in the input type, we can choose the elasto-plastic without or with hardening. So for the S235, for the yield stress, we've input 235 megapascal. For the second one, it's 275, and for the final one is 355. After defining the material behavior, we define a nonlinear combination. So we already did it. In the nonlinear combinations, we can see a single nonlinear combination with the only load with LC1, the only load case that we have defined in this example. We have already run the calculation, and to be able to see the results also, we have defined some sections on these 2D elements. To see the stresses, we go to the 2D stresses. At first, we'll begin with the linear calculation with by seeing the results of the load case LC1, and for the type of values we choose the principal stresses sigma E plus. So as you can see here, we have exactly the same value, which is 426.2 on the left edge, for example, megapascal for the three elements, because here the behavior is elastic. Now we will see the results with the nonlinear combinations. So as you can see here, we have different values, and we have approximately 235 for the S235, 275 for the S275, and 355 for the 355. So the plastification appears, and the stress is redistributed in the intermediate part of the plate, which is why the stresses are no longer the same in the three elements. We can see also the total strain with the nonlinear combinations. So we have 0.73% of strain. This strain takes into consideration the elastic and the plastic strain. But if needed, also you can see only the plastic strain. And here we have approximately 0.5%, which is less than 5%. And as you can see on the left edge also, the plastic deformation is greater for less resistant steel. So to sum up, I go back to the presentation. In this example, we have three identical walls with different materials, and we have defined an elasto-plastic vomices without hardening behavior for all three of them. First, for the elastic stresses, we have exactly the same value for the three elements for a linear calculation. For the plastic stresses, the results with the nonlinear combination, we can see that the value is approximately equal to the plastic limit, and there's a redistribution of this stress in the intermediate part of the plate. After, for the total strain, which is elastic plus plastic, we have a greater value for the less resistant steel. And finally, for the plastic strain, we have 0.537%, which is less than 5%, so the strain is okay. The second example, I'll go back to SCIA. So it's beam on three supports. As you can see, we have defined a beam, but using surface elements, because as I've mentioned before, the plasticity is not yet implemented for 1D elements. So, like before, we should go to the project settings, to the functionality, activate the non-linearity, and the general plasticity in SCIA. So here, as you can see, we have three different supports defined on the edge, two on the edges, and one in the middle. For the material here, we can filter on the used material, so is S235. We have defined a isotropic elasto-plastic vomices behavior when the input type elasto-plastic, and for the yield stress or for the limit, the value is 213.6. So it's 235 divided by gamma m0, which is equal to 1.1. So that's how we've obtained this value. And for the loads, we've applied a surface load on the top flange with a value of minus 60 kilonewton per meter square. And of course, we have defined a nonlinear combination that contains this load case. For the results, we can go to the 2D stresses, and first we will see the principal stress sigma E minus under the load case. And as we can see, we have a value of 374.6 megapascal, which is higher from the value, the limit, elastic limit that we have defined in the materials properties. We'll move on to see the results with the nonlinear combinations, CN1. And here, as we can see, we have a value of 213.6 megapascal, which is equal to the elastic limit. And as you can see, we have a concentration of the stress on the supports, and it's redistributed elsewhere. We can also see the elastic and plastic strains directly here, but also you can go to the 3D stresses, and here you can find the principal plastic strain under the nonlinear combination, and we can refresh. So we have a value of 1.2%, which is lower from 5%. So it's okay. To sum up, I go back to the presentation. So we've seen that you have defined a beam on 3 supports using the 2D elements. And for the elastic stresses, we have a value of 374.3 megapascal. For the plastic stresses, we have 213.6, which is equal to the limit that we've defined in the materials properties. And for the plastic strain, we've obtained 1.2%, which is lower from 5%, so it's okay. The next example is a base plate connection. To show it in SCIA, we've defined the column and the plate using surface elements. For the column, we've used a S355 material, and for the plate is S275. We can go to the materials properties to see the behavior that we have defined. So we can filter by the used materials, and here we can see that for the S275 and the S355, we've defined an isotropic elasto-plastic vomices behavior, an input type elasto-plastic, and with a yield stress and uniaxial tension limit 345 for the S355 and 265 for the S275. We've also defined surface support and point support also, which is rigid in tension only in the Z direction. Here we have a different type of nonlinearity, which is compatible with the plasticity. So we've applied 2 loads, one vertical and one horizontal. Moving on to the results, I'll hide this element and deactivate the volume, the shading, and first we will see the 2D stresses under the load case LC2. For the principal stresses, sigma E minus, if I refresh, we have a value of 797.3 megapascal, which is higher from the 2 limits that was defined in the materials properties. We can also see the plastic stresses, so we should go or change the type of load to the nonlinear combination, and we can refresh. So here we have 344.7 megapascal, which is equal to 345 megapascal, which is the yield stress that we've defined in the material properties. And we can move on to see the plastic strain. You can see it directly in the 2D stress strain, or you can go to the 3D stresses, and here we can directly see the plastic strain. So we can refresh, and we have a value of 4.6 times 10 minus 4 for the plastic strain. To sum up, I go back to the presentation. So in this example, we've seen that the limit was 345 megapascal, and the material behavior is isotropic elasto-plastic vomices behavior. First, for the elastic stresses, we have a value of 797.3 megapascal. For the plastic stresses, we have 344.7 megapascal, which is approximately equal to the limit. And finally, for the plastic strain, we have a value of 0.046%, which is lower from 5%, so it's okay. The final example is a beam-column connection. The beam and the column were modeled using surface elements. Also, we have defined an end plate using a surface element with openings to be able to define the bolts. I go to the library, the materials, to see the used materials. So we have the S235, that it's the material for the column and for the beam, which is the material behavior is isotropic elasto-plastic vomices with a yield stress 235 megapascal. The second one, 8.8, is an elastic material which was used for the bolts. So I go back to the model, and also, of course, we've defined a support here, and we've applied a load, a surface load, at the edge of the beam with a value of minus 43.13 kilonewton per meter square. And to ensure the contact between the end plate and the column, we've defined a rigid elements, these elements, with this cross section. So we can see it directly here. It's a rectangular cross section that with a beam nonlinearity that is in compression only. So for this element, we've used this material, the dummy material, which had a low unit mass and high rigidity. We've defined also two nonlinear combinations. The first one, which contained the load, and the second one, we've multiplied the load by 35. In the project settings, in the functionality, we should also activate the beam local nonlinearity because we have a nonlinearity in the project which is the compression only for the rigid elements. So now we'll move on to see the results, the 2D stresses, and first, the principal stress sigma E plus under the combination CO2. So here we have a value of 505.8 megapascal. We're going to see the results under the nonlinear combinations. So for the first one, NC1, if we refresh, we have a value of 16.2 megapascal. For NC2, where we have multiplied the load by 35, we have a value of 235 megapascal. So we can say that the plastification is reached. We can go now to see the plastic strain in the 3D stresses. So first I'll begin with NC1. As you can see, we have a 0 value because so we don't have a plastic strain. While if we see with the second one, we have a value of 1.2% of plastic deformation. If we zoom here, we can see that this value is obtained in the web of the column, and it's okay because it's lower than 5%. To sum up, so in this example, we have modeled the column and the beam using surface elements with the same thickness of 12 millimeters. After, we've also modeled the end plate, and we've used the opening on 2D elements to define the openings in the end plate. After, to ensure the connection between the end plate and the column, we've defined a dummy members in compression only. And after we've defined also the bolts in the openings using a rectangular section, using a circular section, and also to ensure the connection between this dummy element and the openings, we've used rigid links. So as results, for elastic stress, we've obtained 505.7 megapascal. For the plastic stress, we've obtained 235 megapascal. And for the plastic strain, it's 1.197%, which is lower than 5%, so it's okay. To conclude, the plasticity in SCIA Engineer is suitable for all surfaces. We have seen that we have 4 plasticity criteria in SCIA. For the application in SCIA Engineer, we should first activate the plasticity functionality in the project data, define the behavior of the material and its properties, and we should run, of course, a nonlinear analysis. What we should know also that in SCIA we have no strain limits, so it's up to the user to verify if it's lower or higher than 5%.
And thank you for your participation.